Okay, today we're going to continue our lecture on solutions. We've got 4 major topics we're going to cover, and then we're going to really go in depth here with concentration, which is where we're exiting today. So we're going to talk about miscibility, saturation and supersaturation, or supersaturation, solubility, and concentration with a focus on molarity. But there's going to be 3 other versions of concentration that we're going to talk about here. So let's start with miscibility. Okay, miscibility comes from liquids. Miscibility is the ability that some liquids have to mix in any proportion. Okay, and the classic example is alcohol and water. So we've got okay. And so, water and alcohol can completely dissolve into each other regardless of how much there is of the two materials. So you can have a 100%, well, obviously you can have 100% water, 0% alcohol, but let's say you change your proportion here and you do like a 30% alcohol, which then would make it how much water? 60%. Try again. 70%. Okay. Nice one, Mr. Eagles. Okay. Right. So you could easily have a 70% water, 30% alcohol solution. That, by the way, would be 60 proof. Okay, for those of you that are interested in that sort of thing, which is hopefully none of you. Okay, or you could go the other direction. You could have 30% water, and you could have how much alcohol if you have 30% water, Joseph? Joseph? Good, 70%.
No, I'm thinking of the special triangle.
No, not 30, 60, 90. No. Okay. So it doesn't really matter. You can have any proportion of alcohol and water, and because it is miscible, you can have any of these proportions. All right, they freely mix with each other. Okay, you have other. Okay, the opposite of this is immiscible. Two M's, immiscible. Immiscible. Examples of immiscible are oil and water. That they will not mix. They will not blend. Does it blend? They will not dissolve into the other one in any proportion, in any way. Even the tiniest amount of oil will separate itself from water. And this is the reason these are immiscible. Are exactly the same reason why we get the lipid bilayer that we had from our previous lecture. So we have the long lipid chains that are immiscible in water, and so they stay away from. They try and get as far away from the water as possible, and you get the phosphate heads on either side, and those are miscible in water. Those will dissolve in the water, and so that's how you get this lipid bilayer. Okay. That's miscibility and immiscibility, and that's really about it. Just the fact that either they don't mix at all, or they can mix in any proportion, and they're opposites to each other. Okay, which brings us to saturation. Okay, saturation. All right, our definition now is when a solvent when a solvent has dissolved a maximum amount of solute for a given temperature, it is saturated. When you have as much in there as you can possibly have. Oh, sorry. Yes. Yeah. Big waves. Big waves get my attention, or just shout it out. So don't worry about that. Okay. Okay, so that's what saturation is. That's it. Okay, an unsaturated solution. You guys got it? Or give it another couple seconds. Okay, an unsaturated solution. One of the beautiful things of video is you can go back and watch this again. All right. Unsaturated. Okay, an unsaturated solution Okay, something your PDawg did not emphasize enough is the temperature part of saturation. The solubility is very strongly related to temperature when it comes to dissolving things, and so you need to be mindful of our temperature when we're talking about solutions and solvation, that sort of thing. Okay, now. Then it's possible for that solvent at that temperature. Okay, excess solute excess solute beyond the saturation point of a solution will usually remain undissolved at the bottom of the solution. Okay, and you guys saw this with the model in the PDawg, that if there's more than enough solute, if you have an amount of solute above the saturation point, it's going to start forming a solid at the bottom, or you know, a sediment at the bottom of your solution. Okay. And so the new supersaturated solution. Supersaturated solutions are, that's my best Sylvester. Sylvester, the cat? Okay, yeah. I know that's old school. That's I know. Um, okay. No, I don't want some in there. Oops. Okay, so when a solution at a high temperature is made to be saturated, and then it's allowed to cool, the excess solute may remain in solution. Okay, that creates a solution with more solute than should be possible at that temperature. Okay, so the temperature drops, and now all of a sudden you have greater than your solubility amount. Oh, we haven't talked about that. Greater than the saturation point of stuff. You guys follow me there? Okay, but it remains in solution. Okay, this is called this is supersaturated. It has more dissolved solute. Oh, sorry. It has more dissolved solute than should be in there. Now, I have an example of this. Okay, and we're going to watch a short video that will demonstrate what happens when okay, so you put the original crystal in there, and it starts to cause all of the excess solute to recrystallize and return to a solid state. And so, what would be left behind in that situation? So if you filter out all of that solute out of the supersaturated solution, what was a supersaturated solution, what would you have left? You take the crystal out, and what falls through? Is it just water? it would be the saturated solution, that you would still have solute dissolved in that liquid. It's just no longer supersaturated. That reaction, that crystal reaction, will go until there's no more excess solute. Yeah? Annabelle? Okay. Which brings us to how we quantify this stuff. Okay. And this is solubility. Solubility is a value. Okay, this is a value. It is an amount of solute. Okay, in fact, specifically, it is given by the grams of solute divided by 100 grams of solvent. Okay, often given by 100 grams of water. Okay, so it's how much stuff you can dissolve into 100 grams of water. Okay. This might be an important point. When you have an amount dissolved, okay, at the solubility, so you've matched the solubility of a particular solute, that is the saturation point. Okay, remember, saturation is the maximum amount, previous page, saturation is the maximum amount of solute at a given temperature, right? Solubility is that maximum amount. That is the value. So when you find the saturation of something, you determine what its solubility is, what the solubility for that solute is at that temperature. Does that make sense? No? Okay. So the solubility and saturation, you guys need to be able to make the connection between solubility and saturation. Okay, be able to explain how they are related. Because I'm not going to explain it any further than this. This is a mental exercise for you guys. Be able to explain this connection. Although I kind of bold-faced it for you. All right, which brings us to dun, dun, dun. Concentration. Okay, so we're going to talk about concentration qualitatively. Like, what are we talking about here with concentration? Okay, and then quantitatively, how do we measure it and how do we determine it with numbers? And we've got 5 different ways of describing concentration of something. All right, so I did have you guys identify that solubility of sucrose. You guys remember what that was? 204? Okay, so we're going to write that off to the side here. 204 grams of C12H22011 per 100 grams of water. Okay. All right. So qualitatively, have you guys ever bought frozen orange juice before? Okay, frozen orange juice is the bomb. Okay, you go to the freezer section, you get a can of orange juice. Okay.
Is it like an orange Julius?
It is a great start for an orange Julius. You take like a big old scoop of that and put it in with some vanilla ice cream. Okay, and blend it. Okay, with a little bit of ice. Put some ice with it too. Okay, but qualitative. Okay, frozen orange juice. You can buy it out of the can, and then what do you do to it to make it drinkable? Okay, you thaw it, you pour it into a pitcher, and you add. You should not need to add sugar. Or. Okay, you add water. Okay, what happens? What are you doing to it when you add water to it? Ah. Okay, you do a dilution in order to drink the frozen orange juice. Now, I will say that just taking a scoop of the frozen orange juice is, if you like a really strong orange flavor, it's pretty bomb by itself. But to make orange juice the way it's intended, you dilute it with water and to make it the actual texture. Okay, the actual real concentration of orange juice. Okay, so you need to do a dilution to drink. Yeah?
Yes.
So diluting something is adding water to it, right? To make something to dilute something is to make something less concentrated. It is with whichever solvent you're using to begin with is what you would use to dilute something. Okay. Okay, so dilution then is the opposite of concentration. Yeah? Okay. An example of the flip side. When I make coffee in the morning, I put a dash of salt into it. Trust me, it's really good. It adds just a little bit more flavor to the coffee, and it brings out, so it's excellent. Now, why do I just do that rather than bring in, a cup of seawater and put it into my coffee?
Salt isn't as concentrated as seawater?
What's that?
Salt isn't as concentrated as seawater?
Well,
Or it's not
my tap water isn't as concentrated, but that's the key word we're looking for. Okay, so if I were to use seawater to brew my coffee, that would be really freaking salty and disgusting, and it would be too concentrated for our purposes, right? So that's how I want you guys to think about concentrated and dilute. If you have something that is dilute, that means it has very little solute for its solvent. So if we're going to study this more specifically, we're going to do this in a quantitative way. Okay, now we start looking at our different versions of concentration that we've had before. All right. So the first one we started with was our solubility. Okay, so we're going to keep using our solubility of sucrose for the rest of this, just as an example, as a base value for a concentration. So our solubility remember, this is the maximum right? So solubility would represent the maximum concentration, right? If that's the most that we can dissolve, that represents the maximum concentration. Yeah? You guys follow that logic? Okay. So, what is it? Well, for solubility, then it's the 204 grams of sucrose in 100 grams of water. Now, you may remember, if we set our Wayback Machines to the beginning of the year, that we talked about this value right here, right? Okay, this right here, this amount. How much was this? How much space did this occupy?
1 liter.
What is the volume? It was 1 liter of space, right? And if we filled this space with water, it would have a mass of 1 kilogram. What 1 gram is like a paper clip, guys. Okay, so this is 1 kilogram, and it's also one liter. And so this is actually the definition of the density of water. The density of water is 1 kilogram per liter, or it is 1 gram per milliliter. Okay, so the density of water is 1 gram per milliliter of water. Well, if this is 100 grams of water, how many milliliters is that? It's 100 grams per milliliter, or 1 gram per milliliter. So if this is 100 grams, it would be 100 milliliters, right? Okay, so the next version of concentration that we have on the list is grams per liter. So we're going to take our solubility and we're going to convert to grams per liter. Okay, and so grams per liter, we're going to go 204 grams of sucrose for every 100 grams of water, but that's really equal to 100 milliliters of water. And how many times can we put 100 milliliters into a liter? In other words, how many decimal places off is it? Okay. It's this many. 1. There are 1,000 milliliters in a liter, and if this is 100, okay, so we multiply by 10. So we multiply by 10, that's going to equal 2,040 grams of sucrose into 1 liter of water. So not only is this the solubility of sucrose, this is also its concentration in grams per liter if it is saturated. Does that make sense? Okay. If you've ever tried to make rock candy, okay, you have to add a whole lot of sugar into your water. And when you do rock candy, you make a supersaturated solution. Okay, you supersaturate the sugar into the water, and you let it cool, and then it crystallizes onto the string or whatever that you have suspended in your beaker, or in your cup or whatever you're using for it. And all of the excess crystal, as it cools down, joins up with the rest and creates the rock candy. Okay, so that's grams per liter. Okay, which is 2 kilograms of sugar for every liter of water. which is kind of crazy. All right. The next one is parts per million. Parts per million, also known as ppm. All right. So let's stick with grams per liter per minute. There are, so okay, remember this? That a liter would be 1,000 grams of water? Yeah? So if we have something that is 1 gram per liter, it'd be 1 gram per 1,000 grams of water. But if we were to turn this into milliliters, then we would have 1,000 milligrams into 1. Okay, well, 1,000 milligrams. Okay, in 1,000 grams of water would be 1 gram per milliliter. Well, this 1,000 times 1,000 is 1 million. So a part per million is really just 1 milligram for every liter of water. Of water, H2O, and it's always water, because that's the only thing we do that conversion with. All right, so essentially parts per million is equal to 1,000 times the grams per liter. You guys follow? Okay, so parts per million equals milligrams per liter, or it's 1,000 times the grams per liter to make it milligrams per liter. Okay, this one's a pretty easy calculation. All right, finally, molarity. The one you've all been waiting for. Molarity is defined as moles per liter. Okay, this is the one that we will generally use when we are talking about concentration. We use a capital M to say, okay, and this is pronounced molar. Okay, so if we have a 2 molar solution, that means it is 2 moles for every liter. All right, so what we're going to do is we're going to calculate the molarity of our sucrose solution. We have 2,040 grams per liter. Okay, we got that from earlier on the page. Okay. Well, we can leave liters the same, but what we don't know is how many moles this is. So how would we find out how many moles this is? We need to divide this number by the molar mass. Put it on the bottom. So that means we need to find the molar mass. And that's big, because sucrose is C12H22O11. Okay, so 12 times 12 equals 144. 1 times 22 equals 22. And 16 times 11 is 176. We add those up, we get 2, carry the 1, 9, 10, 14, carry the 1. 342 grams of sucrose equals 1 mole. Yeah?
Yeah.
Okay, so we find this, 240 divided by 342 over liters, and that will give us our molarity for this solution. So we've got 2040 divided by 342 equals 5.96 moles per liter, which equals 5.96 molar. Okay. The other way, okay, so that's this. The other way we talk about the concentration of, we have a symbol that means the concentration of a substance. We put it in brackets, and that means the concentration of sucrose in moles per liter. Or we shorten it to the concentration of sucrose. If we write that, that means the concentration of sucrose, and we usually use molarity anyways. Okay, and that's what this whole thing is molarity. Okay. We are almost done. Almost done. We now have percent composition. Okay, percent composition. Here's percent composition. It is defined as this. It is grams of solute divided by grams of solution. Grams of solution is the total mass of your solution, not the mass of your solvent. All of the other ones are mass of your solvent. This is the mass of the whole thing. So, if we are doing 2040 grams per liter of water, okay, our percent composition is going to be this. So our grams of solute, which is 2040 grams divided by 2040 grams, because that's our grams of solute, plus grams of solvent. Right? The whole thing is in the solution, and so you're going to take the mass of everything that's in there. And that's going to equal 67%. Does that make sense? Okay, any questions on these? All right, that's as far as we're going to go today.